Hi everyone, it's a pleasure to meet you all again. Today I'm going with my colleague Evangelos to present our work, which is called On ADS-B Sensor Placement for Secure Wide Area Multilateration. This project is done by a collaboration between us and our colleague Bryce, under the supervision of Professor Christina Pepper. Thousands of flights are flying across the world per day. Air traffic is controlled by the air traffic control system that keeps tracking these flights and makes sure that traffic is going in a smooth way. Once the aircraft departs from the source airport to the destination airport, it will start sending its information like their location, speed, to the air traffic control system to control the aviation system and take the proper actions. Each message is broadcasted by the aircraft and it will be received by all sensors in the ground stations that are within the coverage area of that aircraft. Nowadays, commercial aircraft use a new protocol to broadcast its information, which is called ADS-B protocol. It uses ADS-B out service to send its information to be received by sensors on the ground or other aircraft who have ADS-B in. As a feature for this protocol, all of these messages are transmitted through an open channel without an encryption, so the communication will be faster but not safer. There are some organizations that collect and keep ADS-B messages. OpenSky is one famous example of a network of receivers, which is a collaborative research project aiming to collect this data and keep it open for researchers. For this project, we use ADS-B traffic that is provided by OpenSky. The open nature of ADS-B arises the need to take security measurements to make sure that the messages have not been modified through its way. For security reasons, verify the received location by ADS-B message is a must. Therefore, multilateration or MLAT is one of the famous examples that could be used for such a purpose by using time difference of arrival. But in fact, it faces some challenges, like the messages have to be received by at least 4 sensors to make the cross-check on the location. Also, its derived and computed location is subject to several noises that are caused by the misplacement of ADS-B sensors or environmental factors. In this presentation, we are going to explain the sensor placement problem in details. We will discuss also 3 scenarios of interest. Also, we'll explain our system model and solution that we are based on to solve the proposed problems. As we observed from the downloaded data from OpenSky, there are geographic areas without ADS-B coverage. We mean there are no available sensors within the range of that aircraft to receive this message. Also, there are other areas which are over-densified by sensors. This figure shows where the sensors are placed. As we can see, the distribution of these sensors doesn't cover the whole area. This situation affects the flight tracking system. Also, it makes security checks like MLAT is not applicable, since as we said, MLAT requires 4 sensors at least. Moreover, the over-densified area of sensors affect on the received signal strength, which increases the noise. As a consequence, this leads us to study 3 scenarios. First of all, we assume there is an area and we have to cover this area with ADS-B receivers. So we need to know the minimum number of sensors and their locations that are required to cover this area. When we say optimally covered, we mean each air point should be covered by at least 4 in-ground sensors to provide MLAT check for every received message. Then we study the scenario where we already have a set of deployed sensors and we need to know where to place any new sensors that are chosen from a predefined set of candidates. Finally, we study the case where we have to select the best set of sensors from already existing sensors at a specific known locations that are proposed by volunteers, which give us near optimal solution. More details about these scenarios will be explained later, but for now we have to understand some concepts that we base on to design our model, which will be discussed by Evangelos.
Hi, my name is Evangelos, and I'm going to discuss a few important aviation metrics as well as the genetic algorithm that we used in our approach. ADS-B signal propagation. In order for the ground sensors to successfully receive the transmitted messages, the line of sight condition must be met. Sensors that do not comply with this condition are considered out of reach for the aircraft. As you can see, the message reception depends on several factors, such as the emitter power, antenna gain, Earth's curvature, and environmental obstacles like mountains and buildings. Time of arrival localization. Let's consider a single aircraft emitter that broadcasts messages and 4 deployed sensors. Given the true emitter's location noted as P, the time of arrival measurement can be described by the mathematical formula presented on this slide. The estimated value for P is given by solving the system obtained from 3 time of arrival differences. Of course, the accuracy of this estimation is affected by measurement errors, which we have to take into account. Geometric Delusion of Precision, GDOP. The formula presented on this slide is used to calculate GDOP. This calculation requires B matrix, which consists of direction cosines, noted as small b's. Now, to derive this matrix, we will need the aircraft's location and the pseudo-range measurements taken by the 4 sensors. It is important to also mention that we need to decrease GDOP as much as possible in order to improve MLAT's accuracy. Therefore, we should avoid placing sensors too close to one another, since this situation will degrade GDOP, eventually leading to high errors. GDOP is a vital part of our fitness function in the genetic algorithm, so we will talk about it again later. Sensor Deployment Optimality Criteria. Here we present several statistical techniques to create optimal designs. Optimal designs allow parameters to be estimated without bias and with minimum variance, thus reducing the costs of experimentation. Moreover, we have the Kramer-Rao lower bound, which gives a lower estimate for the variance of an unbiased estimator. So, estimators that are close to this bound are more unbiased, thus more preferable to use. In our work, we focus on A-optimality. Our main goal is to minimize the mean squared error on the location estimate. Mean squared error will be explained later as we use it in our genetic algorithm. The genetic algorithm. As you may know, genetic algorithms are used to solve optimization problems, and our case is not an exception, since we are trying to find the best possible setup of sensors. On this slide, you can see the internal functions of the genetic algorithm together with a small example. Initially, we have a random population or a highly unoptimized population coming from our dataset. In this case, we assume that there is a population of 3 individuals representing 3 sensor setups. Each individual comprises 4 genes, and each gene represents a specific sensor on the ground with a unique ID. Next, the individuals will be evaluated by the fitness function, and all of them will end up having an assigned score. Through natural selection, we make sure that only candidates with the best score may reproduce and pass their genes. This, according to Darwin's theory of evolution, is the survival of the fittest individual. For us, candidates with the lowest score will be selected, which is something that I'm going to explain in the next slide, hence keep it in mind. So, yellow will be rejected and the other 2 will continue to the crossover procedure. In crossover, the 2 individuals exchange their genes, creating new individuals, meaning new sensor setups. Kindly note that after many repetitions and generations, duplicates may exist. Moving on, mutation is a process that happens occasionally, changing one gene, meaning one sensor, to add diversity in the population. Furthermore, through elitism, we keep the best individual from the current population. Finally, we combine these 2 outputs of the previous processes to create the new population. The whole process continues according to our needs, and the way we parameterize the genetic algorithm. The fitness function. The fitness function is one of the most important parts of this work. We have to define it correctly in order to get the desired results. Now, I have already mentioned that GDOP needs to be reduced as much as possible, but how much? Well, a strict rule could be 0. This means that near optimal sensor setups must have a GDOP that converges to 0. Therefore, a subtraction between this GDOP and the strict GDOP is a good indication of how well the sensors are placed on the ground. As you can see, in the first equation we make use of this subtraction between a calculated GDOP and a required one. With respect to A optimality, we utilize the mean squared error for this subtraction. So now it makes more sense. The closer the calculated GDOP of an individual to the required GDOP, the lower the mean squared error, and consequently, the lower the fitness score. That is why we keep only individuals with the least score during the natural selection. Nevertheless, we further optimize the fitness function by including a cost function and eventually by fusing these two equations together into a weighted fitness function. Now, if we think of the deployment area as a two-dimensional grid of L rectangles, where each can either be assigned a sensor or not, then a knapsack equivalent formulation would be to select as few rectangles as possible, while at the same time minimizing the GDOP. This is what the cost function stands for, which is used to force the genetic algorithm to find better results. In the end, we make use of the Pareto weight to fuse and calibrate the first two equations into the final fitness function.
Now I will describe our system model and explain how it developed to solve the sensor placement problem. Our system model is mainly based on GDOP evaluation principles. In more details, it assumes that we have a volume space A, where we select M sample locations within this space. As Vagarius explained, the GDOP value should be minimized to have a high MLAT accuracy. In an ideal situation, the required GDOP should be equal to 0. Although a GDOP of 0 is hard to achieve in practice, we may want the sensor deployment to attempt to determine this as close as possible. While few applications are okay with a small GDOP value, so they specify a tolerance value that the GDOP could not pass. So we define the required GDOP for all set of samples locations. Also, we assume there is a set of sensors that are placed on ground. As an aircraft passes the airspace and crosses one of these sample locations on space, it will broadcast ADSB message to the sensors on ground. As long as the message is broadcasted, it will be received by all sensors that are within the line of sight of this air point location. Now we have to evaluate the GDOP for each air point on volume space A. Let's assume the sensors are placed already. Then the process to get the minimum GDOP for each point based on this setup is done through 3 steps. First of all, for each point, the list of sensors that are within the line of sight of this point is defined. Then, in the second step, the cardinality of sensors is checked to know if the number of sensors that receive this message is less than 4 or not. If yes, then the achieved GDOP will not be computed, since as we said, MLAT requires 4 sensors at least. Finally, the achieved GDOP value for the rest of points will be computed for all 4 size subsets of sensors, and the achieved GDOP will be given to the minimum value. As our objective function is to cover the airspace with a minimum number of sensors with a minimum GDOP values, the mean square errors or deviation between the achieved and the required GDOP in the entire airspace is computed, and this function is used to solve the sensor placement problem as an objective function. To discuss our model in details, we propose 3 case studies, or we can see them as problems that have to be solved, and then we show how our model solves them. In the first scenario, which is called optimal sensor placement from scratch, where there are no sensors are placed, we assume the airspace A has to be covered. Again, when we say is covered, we mean each point should be within the line of sight of 4 sensors at least. Then, we assume that we have a budget of N sensors, that we should place them in the right places. As an example, if we have only 4 sensors, where should we place them to optimally or suboptimally cover the selected airspace? At this location, or these locations, or these locations? To solve this problem, we generate a number of sensors as candidate sensors where they are distributed uniformly on the ground of the selected area. Then we use our objective function of minimum GDOP value with the genetic algorithm to get the locations of the 4 sensors that we have. In the second scenario, we assume that we already have a set of deployed sensors in the ground, and we have to know where to place any new sensors to cover the airspace. As an example, if we have 4 deployed sensors, how many extra new sensors are needed to cover A, and where should we locate them? So how we can solve this problem? As we did in the first problem, we uniformly generate a set of sensors as candidate locations and combine them with the already deployed ones and use the genetic algorithm with the all deployed and new sensors to get the best new sensors and their locations. Finally, in our third case, we study the scenario where we have a set of proposed sensor locations by some volunteers, and we have to select the best N sensors of them that could be used to cover the airspace. As an example, if we have 8 proposed or deployed sensors, then we should know which ones or the minimum ones that could be selected to cover the airspace A. Again, we use the genetic algorithm with the minimum GDOP objective function to get the best solution. As Vagelius explained, genetic algorithm is used to get us the best near optimal solution. Our result proves that, as Vagelius will explain to us by the next section.
The figures of this slide show the simulated K coverage at 3 different altitudes for a real-world random placement of 30 sensors. The fitness score of this placement, obtained by simulation, is approximately 0.35. By looking at the figures closely, it is crystal clear that this placement is not optimal because of the poor K coverage and because GDOP distribution is mostly 60 and above. These are also indications of overdensification of the receivers in this area. On the other hand, we have the results from the genetic algorithm for case 1. As you can see, most of the GDOP distribution is below 16 with a very high K coverage. In addition, the associated fitness score is approximately 0.007 for only 10 selected sensors, starting with a completely random population since the deployment is from scratch. Now, to get the results, we parameterize the algorithm as robust as possible. The upper graph shows that it converges to the best solution after 10 generations, and the lower graph shows the selected sensors. Kindly note that the minus notation in front of the fitness value is only used to instruct the genetic algorithm to search for local minimums. The fitness value in our approach is always a non-negative value. Furthermore, we have the following graphs for case 2 and case 3 with their corresponding scores. Since these two cases begin with an existing setup, the algorithm is able to find the best solution instantly. That is why it converges immediately. To sum up, in this work, we leverage the genetic algorithm to solve the sensor placement as an optimization problem. We showed that not only we are able to build an optimal deployment from scratch, but also bolster existing ones. Our main goal is to provide security and accuracy.